Okay, so we have um, discussed comparing a one group, one sample against a null hypothesis mean. So we've got one sample, one group against a number. We did the pooled variance t-test. So these are comparing two different variables. So comparing the sample means from two groups with the same variable, excuse me. So height in group one and height in group two, or service in the suburbs and service in the city, assuming the variances were equal. That was the pooled variance t. If we assume the variances are not equal between cities and suburbs, that would be the separate variance t. So now we'll take this one step further and ask, well, what if we are looking at more than just two groups? So city and suburbs naturally is just two, but some situations we might have more than two. So for example, if we're looking at a sample of banking loan data, we might be interested in whether loans differ across regulator type. And there are at least four major regulators of lending institutions, and so that we don't have just two groups, we have more than two. So one way to handle this is just to do lots of pairwise comparisons. So we could take the FDIC versus the credit union regulatory body, and versus so that would be a pairwise comparison. Then you would do another one with the other two, and then the credit union body versus the third and the fourth, and then the third and the fourth versus each other. So you'd have six pairwise combinations for those four groups. And while that would work, it creates a problem. So remember that if we use a 95% confidence interval, we have a 5% chance of a type 1 error every test we run. Well, if we run 6 tests, that 5% chance is now 6 times larger. So that we would take that 0.95, the chance that we get it right, and we would have to do 0.95 to the sixth. And now we've got a pretty significant chance of making a wrong conclusion. And we don't like to make wrong conclusions. We want to minimize our type 1 error if we can. So it would be nice to be able to systematically look at tests with more than two groups. And one way to do that is the one-way ANOVA. So one-way ANOVA is a way to look at. I think the chart here explains exactly what's going on with ANOVA. So you've got a sample of data that has multiple groups in it. So let's take the whole sample, including all the groups. Well, that sample has a sample mean, but individual observations will be different than that mean. So any given observation is going to be different from the sample mean. And in this chart here, we're looking at data point 1, 3. So X is some data there. It's in subgroup 3. So we have 3 subgroups, group 1, 2, and 3. And that big braces, the number 3 next to the big braces, that is the total difference from the sample average for that observation. So for all of these observations, they're going to be different from the sample mean. So there's a pool of variance. There's a lot of there's uncertainty spread throughout the whole sample that of all of these observations being different from their mean, right? And that's going to give us a standard deviation for the whole sample. So anyway, there's a lot of variation in the sample that's not explained by the sample mean alone. Within these 3 subgroups, we have a subgroup mean. So that's this blue x1, x2, and x3. So in group 3, this observation x13 is in subgroup 3, and it's different from its subgroup mean as well, but not as different from the subgroup mean as it is from the sample mean. So looking just specifically within subgroup 3, there's less variation that's not understood in a way. So we can explain more of the variation in subgroup 3 by using a mean specific to that subgroup. So the difference between x13 and the sample mean is described by 3. And some of that variation, some of that difference between the sample mean and x13 is explained by the subgroup mean, and some of the difference is still uncertain. So we have this overall sample variance, and some of that variance is within group variance, and some of that variance is between group variance.